Hi, everybody. I'd like to welcome you to the Altinity webinar on ClickHouse and the magic of materialized views. My name is Robert Hodges, and I'm the CEO of Altinity. And I put together this webinar along with a lot of help from the Altinity engineering team. So just a little bit of information before we get started on the webinar, some things that will help you enjoy it more and also ask questions. There is a Q&A box that you can use that's available to you, and you can post questions at any time. We will see them as the talk proceeds. If it's convenient, we can fold them right into the presentation then and there. Otherwise, we'll have time at the end to answer questions. In addition, this webinar will be published along with the slides afterwards. You'll get a link to it automatically, so you don't have to take frantic notes. Both the webinar itself and the slide deck will both be posted. With that, I'd like to get going and jump into our material. I'd like to give you a quick introduction to Altinity, which is the premier provider of software and services for ClickHouse. We offer a number of things to our users, starting with enterprise support for ClickHouse, as well as ecosystem projects. That includes things like APIs, BI integration, things like that. We do a great deal of work on ClickHouse feature development. Recent work that we have done or are doing right now includes geohashing, new codecs, tiered storage, log cleansing, so on and so forth. We're particularly interested in features that enable ClickHouse to be used by enterprise users. We develop management software beyond that, sort of outside the scope of ClickHouse itself. Probably the most prominent thing that we've worked on is the ClickHouse Kubernetes operator. We've also done talks on that in the past, and we'll continue to do so in the future. If you use Kubernetes, you should definitely check that out. We also have another great product coming out, the Altinity Cluster Manager, which is a cluster manager, GUI cluster manager for ClickHouse installations. We'll be talking more about that next month. And then we do POCs and training. We're the main US and European sponsor of the ClickHouse community. We work closely with Yandex and the core committers of the community to promote the use of ClickHouse and make it as popular as possible. So with that, I'd like to dive in and give a quick introduction to ClickHouse for anybody on the call who is not familiar with it. So ClickHouse is a data warehouse originally developed by Yandex. It understands SQL. It runs on everything from bare metal to the cloud. That includes, of course, containers in between. It's a column store, which is to say, as the picture shows on the right, that the data are stored in columns or arrays, if you will, and every operation on data, particularly data in storage, is sequential. So we have sequential writes, we have sequential reads. We don't ever do random I/O. And in particular, this model is very well suited for, of course, for spinning disk, but it also works quite efficiently for SSD storage as well. ClickHouse is extremely fast, and one of the reasons for that is it does both MPP across nodes, so parallel execution across multiple nodes, and then on individual nodes, it does something called vectorized execution, which means that we break up arrays into pieces and basically feed them onto the CPU using SIMD instructions, that's single instruction, multiple data, so that we can process the arrays as quickly as possible. The data are compressed. The default compression is LZ4, but other compression formats are possible, and there are additional codecs that you can apply which further compress the data and make it more compact. It scales to many petabytes. We typically see people jumping onto ClickHouse as data sets reach into the range of hundreds of millions of rows. This is where traditional open source databases as well as small enterprise databases tend to get a little tired. ClickHouse handles these data sets very, very well and then scales up to many, many petabytes. And there are a number of installations worldwide that run into the tens of petabyte range. As I mentioned, it's open source under an Apache 2.0 license, so there are no particular issues with distributing it in your own software. You can use it any way you like, as long as you observe the terms of the Apache 2.0 license. And as I said before, it's extremely fast, and that's something that we'll be talking about a lot on this call today. But Of course, if you're here to hear about materialized views, you probably didn't want to hear marketing fluff. This is just a level set so that people who haven't met up with ClickHouse before will understand what we're talking about as we dive into the topic at hand, which is actually using materialized views. So this is a very, very powerful feature of ClickHouse. And in this talk, what I'm going to do is just provide you a bunch of examples of how to use it. So we'll kind of capture the theory of how the materialized views work and some of the plumbing behind them as we go through these examples. And I hope by the end of the talk, you'll have enough of a context that you can then really begin to reason about materialized views and use them to solve your own problems. So what I'd like to do now is I'd like to start with a relatively simple use case, which is using materialized views to handle basic sums. So let's just start with a problem, and that is computing sums on large data sets. Now, one of our favorite test data sets is something called the NYC Taxi and Limousine Commission data. It's 1.31 billion rows of data from taxi and limousine rides in New York City. It's an example of a public data set. You can pull it down, you can load it into your data warehouse or database, and you can play around with it. It's a great data set to get a sense of what are the capabilities of ClickHouse or any data warehouse for that matter. So the question that I'd like to try and answer on this data set today with a materialized view is, what is the average number of persons per taxi in each pickup location? So taxis go from a pickup location to a destination, and what's the average number of persons per taxi for those pairs? So this is actually something that you don't have to do anything special in ClickHouse to solve it. You can just have a big fact table, and then you can write a query like the one that I'm showing you here. And that query is, oops, we're seeing my Linux menu bar here. That query is fairly simple. So we're going to select, the key part here is we are going to sum all the passengers, grouping by the pickup location ID. And then we're going to divide by the count of rides in that location ID, and that's going to give us an average number. So just by knowing the sum and the number of taxi rides, we can get the answer. And in this query, I'm just going to limit it to 10 because I don't want to have 10,000 things or more spilling out onto the screen. But when we run this, we see that the elapsed time is 1.8 seconds. And if you're a ClickHouse user, you'll recognize some of the other stuff in that row. It shows we processed 1.1 billion rows, the speed at which we processed it, so on and so forth. This is pretty typical ClickHouse performance. I call this the marketing line. So the question for this talk is, can we make it faster? And the answer, as with many things in ClickHouse, is yes. So what we can do is create a materialized view. And for those of you who have not used materialized views before, a materialized view is like a table, but it also presents a different view on the data that you're interested in. So the basic idea is, in SQL, you can create something called a view, which is kind of like a canned SQL query. But when you run a normal view, it's actually just executing that query. There's nothing special been done to the data underneath. So it's just as if you typed that query in directly, but the view gives you a shorthand that means that you don't have to remember all the pieces of it and can refer to it more easily. In the case of materialized view, we have, of course, the covering view, which gives you, sort of what appear to be columns in the appearance of a table, but in fact, there's a real table underneath it. And as you'll see, that table is then populated automatically from some other table. So we can walk through the definition of the materialized view, and we see that we're creating a materialized view. It's called trip data SMT-MV. It's using something called a summing merge tree. So one of the things about views or materialized views in ClickHouse is that you want to choose an engine that's specifically designed to aggregate data. The normal engine that we use for large sums of data is called merge tree, or large amounts of data. The summing merge tree is a specialization of that engine that's designed to sum data. Like all merge tree engines, we partition the data here because this table could get large. We're going to partition by the month. We have an order by, which is basically going to define the dimensions over which we're summing. We have this keyword called populate, which means when we create the view, automatically pull data in, and then the rest of the definition is actually how to derive the data in that view. So the idea is that that select is going to be run on what we call the source table, the called trip data, and it's basically going to collect the information that we're going to put into the view, group it, and so on and so forth. So this is a basic definition of the view, and so when we execute that, the view will be created, and because we have this populate keyword, it'll automatically be filled with data from the underlying from the source trip data table. Now, once we've created that, we can actually go ahead and run a query, which looks very similar to the original one, which is that we can go ahead and now ask this same question. And the view actually doesn't actually group the data in quite the same grouping as we have in our query. So we're gonna provide a group by. We're gonna go ahead and issue a very similar query. We're gonna sum up the passenger counts. We're gonna sum the trip counts, and then go ahead and run this query. And voila, we see that the query now runs. It gives exactly the same result, which I've left out just because the screen would become too crowded. But we now have reduced the time to get the answer to this query to 16 1,000ths of a second. So in other words, the materialized view in this particular case is 113 times faster than querying off the direct table. So this is a substantial performance speed up, and is actually one of the big reasons, of course, that people use materialized views, because it allows you to get very, very fast answers off common queries basically by pre-aggregating the results. One final thing I'd like to do on this simple example is to now go in and kind of look at what's going on under the covers. So can you add a join in the select when creating the materialized view? I don't believe you can, actually. That's an interesting question, and I didn't test that. But one of the reasons you can't add a select, that a join wouldn't really work, is that when the view, in fact, this table this picture that we're looking at will show it. The view basically executes every time a new part is added to the source table, and so it's going to process the data in that source table. If you had a join, it wouldn't be really clear how you would actually be able to merge the data into the target table. So that's an interesting question, but views are really designed to summarize data that you already have in a single table. And here's basically how it works. So we have a table here. Oh, I see we have the table here is labeled as CPU. It actually should be trip data. But the uncompressed size of that table, or the uncompressed size of the data is 104 gigs. Compressed, it's 43. So the idea is we created that view. Every time something is put into the trip data table, is inserted in, a trigger is automatically executed. And that's really what a view is. It's a trigger on a source table. And then what happens is it goes and puts it in this kind of funny looking .inner trip data SMT MV table. And this is a table that's actually created automatically when we actually run the create materialized view command. So and what we see here is you get an enormous amount of compression because we're summarizing the data. So the compressed size and the uncompressed size in both cases are something like, well, more than 1,000 times smaller than the original table. And this is one of the principal reasons why materialized views are extremely fast. So we can do selects directly off the trip data table on the left. We can do selects directly off the view. We go directly to those, but then but for the right case, you can think of it as an insert coming to CPU, firing a trigger, and then circling around, and the summarized data then gets added into this summing merge tree table. So I hope that answers that question and also gives you a little bit of background on what's the plumbing underneath the views. So let's keep going. So the next thing is generalizing this. So that the summing merge tree is really designed just to sum numbers. And it's kind of nice because the syntax that we use to create the view looks very similar to SQL syntax, and you don't have to think a lot about what's happening. The view was created. It did the background work to create aggregates. It also created the background table that it populates into, so you actually didn't have to do a lot of work. Now, if we want to generalize this to other types of SQL aggregates, we have to do a little bit more work. And I'd like to dive into this use case now because this is more closer to the way that views are actually used for real use cases. And because what we're going to do is look at aggregates other than sums. So in this case, we're going to come back and we're going to ask the question, can you give us for example, the minimum, average, max, and then the sum of fare amounts for all taxi rides out of the trip data table. And we have a where clause here because there's actually a little bit of dirt in this table, if you will. So I'm restricting the fare amounts. They've got to be above 0 and they got to be less than 500. It turns out there are some negative fare amounts, which presumably are bad data. So we're going to have a filter in here to remove that data. And when we run this query on the basic fact table, it's going to take almost 5 seconds to run. Processes 1.3 billion rows. It's a fairly expensive computation, and of course, if you were ClickHouse will of course scale to much larger amounts of data, in which case this would become very expensive indeed. So the question then obviously is, can we make this general aggregate case faster? And as you'll see in this talk, we don't usually ask questions like that at Altinity unless we can answer them positively. So let's see how we do that. So what we're going to do now is we're going to create a view for all aggregates. And this is going to be more complicated. So we create the materialized view. We're going to use that same summing merge tree engine, which will also do general aggregates and not just sums. We tell how to order it. And in fact, the first part of this view is really going to look identical to what we previously did with that simpler case. But what's interesting here is I've added a couple new things. We have these min state and average state and max state functions. We also have a filter condition. So in the view, we just discussed that you can't really do joins because they don't make sense, but filtering conditions of course make sense. That this is something that's selecting data within or filtering data within a single table. So in the view definition, only data that actually meets this condition will get put into the materialized view. What's really interesting though is these state functions, because what these are doing is they're actually computing what's called a partial aggregate. And this is a special formulation that, as far as I know, is unique to ClickHouse, but it's a way that we must define the view in order to allow ClickHouse to compute the aggregates correctly. And what I'd like to do is just take a short digression and talk a little bit about how aggregation actually works in ClickHouse. So if you think about the progression of the data as going to an aggregate that you can add, for example, the average cost of taxi rides, we can start with a single row which has a fare amount in it. And that's your source value. This is the thing that we want to aggregate. For example, take the average over 1.3 billion rows. There's this average state function, and what this does is it translates the data from some number of rows with fare amount into what we call a partial aggregate. And this is a value that actually sits in the table, but you can't query it. If you go to the materialized view and you try to query this result directly, you'll just see garbage, kind of funny characters and so on and so forth. And this can be really confusing when you first see the materialized view. What you actually have to do is you have to tell ClickHouse, hey, in this view, I'd actually like to see all the partial aggregates merged into a single value. And so there's if you will, a twin function called average merge, and that says, hey, take all the partial aggregates that you have across all the parts of data, because remember, if you're a ClickHouse DBA, you know that data is split up into a bunch of parts. So take all those parts with all the partial aggregates and put them together and give me a new value. And that's something you can actually select. So that's why I have the smiley faces. These are things we can select. The middle one you can't select, or at least you can't get any useful information. And then when you do the average merge, you have something you can select again. So this is a very basic flow, and you'll see this in almost every, you'll see this in some form in almost every interesting materialized view. So using that information and with that knowledge, we can now select from the materialized view. So we go ahead and construct our select statement, and instead of actually just selecting values or using a sum function or something simple like that, every value that we're interested in, we say something like min merge or average merge or max merge, and that gets us the actual values. And that will get us exactly the same results as we got from our previous query directly on the fact table, just slightly different syntax. And the result in terms of speed is phenomenal. So this really, this speeds things up by something like 274 times. So it's an enormous increase in the efficiency of the query. We're down to 17/100ths of a second. So in the description of this talk, I originally said we could speed things up 20x. We raised it to 200x because otherwise we felt you wouldn't believe us if we were so far wrong. These views can have an enormous impact on performance. So that is pretty, sort of a pretty basic usage of queries. And I think in many use cases, this is perhaps the most common use case is to just aggregate information, because ClickHouse just makes it very, very simple. And of course, the results are blindingly fast. But there's actually other ways that views can be used that make them useful and, in fact, a unique capability of ClickHouse. One of the more interesting use cases is something that we call a last point query. And to illustrate this, it's helpful to have a picture. So this is a common type of problem that you get in time series. Let's imagine that we have a data center and it has a bunch of hosts in it. It could be a cloud, could be anything, but the point is that you have VMs or actual racked hosts, and they generate at intervals, say every 10 seconds or so, they generate a record that shows their exact CPU utilization. So you can imagine a flow of these CPU records coming into this thing that we call the CPU table. That's just how we're modeling it. And at any given time, you could have, say, a week's worth of these records. Your question is, what is the current CPU? I don't care about the average over the last week. I don't care about what was the max. I don't care what was the min. What is the CPU utilization right now? So in other words, what was the latest measurement that we got from each host? This is the last point problem. Now, in ClickHouse, we can solve this using a subquery. So basically, we have a select, and the way that we're going to compute this is we can get this value called usage idle, which is just like, hey, how much of the CPU capacity is idle right now? Subtract that from 100. That basically gives us our actual usage. That's the things that we want. Now we can, but the query that we have to use to get that is a little bit complicated. We're going to first of all find what was the latest in the middle here. We're basically finding out what was the latest value of each of the measurements from each host. In other words, what's the set of last measurements from the host? And then we're going to scan the entire data set, and we're going to ask the question, hey, do you match? Are you at that time, and do you match the host? That's the tags ID. And then we're going to pop that row into the data set. And then we'll finally do a join on the outside to give it a nice host name instead of a number. So this query is, we're not trying to make this query look bad. We've basically done everything we can. There's an index being used in the inside query. We're optimizing nicely. This join, we're basically doing it at the end, so we don't have to join a lot of data. But in the basic query, we're going to have a table scan. There's just no way to get around it. ClickHouse is going to have to go look at all the values to see if they match. As a result, this query is fairly slow. You can see the amount of, we don't actually have a terrifically large data set here. This is actually from the time series benchmark suite. It's a data set or a benchmark data set developed by one of the other time series databases. And in this particular example, we're going to run in a little over half a second. And we'll get the output that we're looking for, but the point here is that this should really be very quick because there's actually 4,000 hosts in this data set. We should be able to just get those last records and be done. That should be really quick. So can we do that? Well, once again, the answer to this is yes, but we're going to have to take a little bit different tack from the previous materialized view that we looked at. So in this case, we're now going to define the materialized view in a slightly different way. Instead of just defining the materialized view and letting it create the inner table automatically, we are actually going to create our own table for it. And so this is, you could call this a target table. And so here's an example of the target table creation. So we're going to go ahead and create the table, so filled with aggregates, and it's going to have these special data types, aggregate function, and that means we're looking at an aggregate here, one of these partial aggregates. So, and these are a little bit tricky to read, so I'm not going to go into too much detail here, but the basic idea is we define the types on the table, define the engine. In this case, we're going to use aggregating merge tree. We're going to partition by tuple, and we're going to order by the host. So let me just explain those. So aggregating merge tree is another aggregating engine. It's pretty much the same as the summing merge tree. We don't really, there's not a lot of difference between them, except the summing merge tree allows you to just use the syntax of the SQL sum function instead of having these specialized aggregate functions. So that's the only difference. And partition by tuple is actually a trick. It means, it tells ClickHouse, it's sort of an idiomatic way of telling ClickHouse, hey, I don't need this data partitioned and I don't need it sorted. And so that's a way of just telling it, hey, don't bother to create a bunch of parts. Just stick it all in one place. And so this is actually a completely new way that we can create the materialized views, and it's actually the recommended way for a lot of use cases for reasons that you'll see later. So we got the table. Now we need to create the materialized view. And one of the advantages of this approach is that it's much simpler to create the materialized view. So here we can see we're going to create the materialized view, give it a name, and then we're going to point to that target table. And when the trigger fires, that's where the data is going to be put. And then all we have to do is give a select. And this select then is going to use a specialized aggregate function called argmaxState. And the idea here is this is going to be a function that's going to allow us to link the created date, the time, as well as this column usage idle with the latest value of creation of the records. That's a little bit of a mouthful to say. Let me show you a picture, because this one, when you first see it, can be very hard to understand. So we have as we showed before, we have this sequence where we start with the source values, we go to partial aggregates, we go to merged aggregates. So if we weren't trying to link things, we would just have created at, we would find the max value for that, and then we would merge it to read it. But what happens with this argmaxState and the average max merge is the middle one in particular allows you to link a value of usage idle with that max created at that you found. So what it does internally is it says, hey, where's the row with a maximum value of created at? What was the corresponding value of usage idle? I'll take that and add it to the view. If it happened there were multiple values, it would just pick one, but in this case, there's only going to be one. So this sequence then allows us to not only compute the aggregate, but then link it with values that are going to allow us to solve this last point query problem. So with that understanding, we can now go ahead and load data do the next step, which is we're going to need to load data into this materialized view. So one of the things about the new way of doing materialized views in ClickHouse, where we use an explicit aggregate table and then point to it in the materialized view, is that the populate keyword is no longer supported. And I actually don't know the design reason for that. It's something that you'll bump into, but I want to mention this. You're basically going to have to do the insert yourself, but it's pretty easy. So basically what we're going to do is we're going to go ahead and insert directly, in this case, we're going to insert directly into the view. You could insert into the underlying table. It doesn't really matter. We're just going to give the select and basically the same form of the select as we had in the materialized view, and wham, it's going to drop it's basically going to process the data and populate the view. So once we've done that, the next thing we want to do is, in this particular case, we might want to create a normal view that hides all this messy argmax merge, max merge, and stuff like that. So we're going to create a view which actually has the select and turns those values with the merge functions into sort of nice values again that are easy to select from. And this is a common approach in this particular use case because it hides a lot of gnarly syntax that you might get wrong. So we create that view, and then at this point we can now do the select. So this is a lot of work, but we can finally do this select, and we went from 566 one-thousandths of a second. We're now at 5 one-thousandths of a second. So this last point view is 113 times faster. And this last point view, depending on the size of this particular case, we didn't have a lot of data to select from. As we saw previously, it was about 31 million rows. Of course, in a real use case, imagine that extends out to billions of rows in your source table. This, of course, would be phenomenally fast compared to doing a direct select. So this is a very powerful approach and an example of how the materialized views do more than just give you simple aggregates of data. It's actually giving you a different view of the data by selecting the last item that was last measurement. And because this has a little bit different form, it's useful to look back under the covers again and see exactly what's going on. So the base table or source table is CPU. That's a merge tree. We do inserts into that. That fires the trigger to go into the materialized view, and then it turns around and puts it into the CPU last point idle agg. And you then see the view on top, so we're selecting through that view just for our personal convenience. That's not necessary, but it's a nice touch. The thing that is really interesting about this particular case is to go ahead and compare the compressed and uncompressed sizes of the source data with the target table of the view. And in this particular case, the amount of data is tiny. So the compressed size is actually going down to 29K. This is a factor of, let's see, do the math on this. This looks like a reduction of something like 100,000. It's a very, very impressive reduction in the amount of data. So very nice feature, very, very useful for getting fast answers to what's otherwise a difficult problem for SQL databases. Let's do one more use case. So we have a question coming up. Can we archive this last point by day to take snapshots of what happened day by day, or will it be replaced as time passes? That's a great question, and I think let me just back up and go ahead and start this. You can definitely archive it. What I would say, if you want to have snapshots of what happens day by day, so first of all, let me answer the last part of your questions. Will it be replaced? Yes, it'll be replaced. So as new measurements show up, they will get replaced. And in fact, important thing about materialized views is the update of the firing of the trigger is synchronous with the insert. So it's not just that it disappears at the time your insert is processed into the CPU table. So you've got another block of, say, 4,000 CPU measurements. You insert them in, the trigger fires. At that point, the view is updated and your old data is gone. So that's a problem. Now, if you want to take the snapshots, then what you're really asking is you want to compute, can I compute a normal aggregate? And the answer is absolutely yes. What I would do in that case, the simple answer, is I would actually have two views. There's the cost of doing this last this last point view is minimal. It's tiny. The amount of data we're actually processing is very small. And so what I would do is I would actually have that view, and then I would make another view which is just computing normal aggregates, perhaps by hour. That would be, and at that point you can create those aggregates, and as you'll see a little bit later in this talk, we can actually drop data out of the source table, but the aggregates you've computed in your views can stay there forever. So you can reduce the, instead of having values every second or 10 seconds for each CPU, you can reduce it to hour, and then you create a volume of data that you're comfortable keeping for years. So I hope that answers that question. We can go back to it later on if you have more. Great. So let's move to this last use case where we're going to look at using views to remember unique visitors. And this is a really cool capability of ClickHouse. I've worked with a lot of databases. I don't recall ever seeing anything quite like this capability, but I'll put it forward. You can judge for yourself. So here's exactly the problem that that I was just discussing, is that if you have very large tables, a common way of processing data where you have huge amounts of sort of low value, high granularity base data, what you'll do is you'll bring it in, you might keep it for 3 days, 7 days, 30 days, something like that, but eventually you're going to want to get rid of it because it's just using up space and it's not that interesting after a certain point in time. So in ClickHouse, there is a new feature called TTL, which works reasonably well. I've used it. It's a very convenient feature. In this particular case, I've defined a table called traffic, and it is going to throw away data after 90 days. So this is the sequence. And so anything that goes into that traffic table, after 90 days, it will disappear. Well, maybe 90 days and 24 hours, because it takes ClickHouse a while to get rid of it. The point is, it's going to disappear. So how are we going to remember the aggregates which are computed off it? So here's an example, is we want to find, I want to know on which hour of the day do I have the most unique visits on a product SKU 100. So here's a query to get that. So I'm going to do a group by hour. I'm going to use this function called unique. And what that does is in the group by, if you give it something that's a non-group column, it will count the number of unique occurrences. We sometimes call these uniques. And so it's a really useful function. And this basically allows us to say, hey, how many unique customer IDs visited or looked at this SKU broken out by hour? Great query. But the problem is, how do we remember, once that data gets truncated out of the base table, how do we actually remember this? Well, we can create a view. So we'll start with using the new style of view, Materialized view, where we're going to create a target table for the unique visit data. And so we're going to call this traffic uniques ag. We're going to store the hour as a date time. We're going to store, and this will be the beginning of the hour, as you'll see. We're going to store the unique customer IDs, and then we're going to store the SKU. So pretty straightforward, aggregating your merge tree, partition by, in this particular case, sometimes these views are so small you can just partition by tuple. In this case, we're definitely going to need to partition, to break it out into real parts. So we're partitioning by month. And so that's our table. And you'll see proof of this in just a second. Now we're going to use unique state. So we're going to use a state function. Unique is the aggregate function. State, of course, is collecting the partial aggregate, just as we saw before. So we're going to go ahead and create that materialized view, gather up partially aggregate the uniques, and then group by hour and SKU. So that's fairly straightforward, similar to the examples we've seen before. And at this point, we can now remember the visitors indefinitely. So, and because the interesting thing is, what will happen is, remember, the materialized view is just a trigger, and the target table that it's aiming at is just a table. So deleting data out of the source table makes no difference to the aggregates in the target table. They'll remain there forever. The flip side of this, which you do have to remember, is that if you deleted something out of the target table, it would not be reflected in your aggregates. So if you have some business reason for this, you have to think of another way to handle this aggregate. There actually is a way to do this, but that's not a use case that we'll handle today. But at this point, we can remember our visitors indefinitely. Now, one issue with this particular use case is this ability to aggregate or partially aggregate these unique visits is very powerful. But you also should know a little bit about what's happening under the covers. What is actually being shared in the partial aggregate, the thing that ClickHouse remembers so it can top these things up long after your data is gone, is it actually remembers a hash table that contains all the visits for a particular set of dimensions in the view. And those hash tables can actually get pretty big. So one of my favorite queries when I'm working with materialized views is this one that's shown up above. This basically allows me to check the size of all the tables in my database, in my current database, show me compressed as well as uncompressed bytes, and also show me the number of columns. And as we can see right here, the traffic table is not super large. Let's see, yeah, so compressed bytes, it looks like it's about 626 megs. It's not a particularly large table, about 1.4 gigs uncompressed. The compressed size of the materialized view table is about a 12th. And actually, if you, under certain circumstances, depending on how you define your partitions, it could actually exceed the size of that traffic table. So this is an example where you do want to check the view and make sure that you're doing something sensible, because actually what that can do is it can create a situation where the view can actually be slower than scanning on the original table. The plus side, though, what you get from that is you remember these values forever. So it's a trade-off. So that completes the roundup of use cases. There are many more, as we'll discuss in a minute, but those I think are four that are useful and should get you started and hopefully cover a lot of ground. I'd like to touch on two other operational issues which are significant for loading, for managing views in production systems. The first is just talk a little bit about loading view data, and a second one is talk about schema migration. So let's talk about loading first. So one of the problems with views, if you have a materialized views, if you're running in a production system, is you may be creating the materialized view and there's data flowing into the system constantly. So one of the problems with, for example, the populate keyword that we showed in the early examples is that while that populate is running, you'll actually miss, the trigger will not fire on any new data that arrives in your source table. That's a problem because what that means is your aggregate is not going to be fully populated. You can also get this if you just sort of casually just run an insert on the data. While that insert is running to populate the view for the first time, you'll again miss, you can miss newly arriving data. So the question is, how do you get around this problem? Because you may have a very active system, you want to add a new view, but you actually don't want to stop ingest of new data. And one way to do this is to think about putting filters on both on the materialized view as well as the statements you use to populate it initially, and they'll basically be based on time. So here's an example. We're going to create this view, and in the view, we're going to put a condition on where we're going to say we're only going to accept stuff after the 12th, after the beginning of the 12th of July. So we're only going to accept future rows. We create this view, and actually for the first couple weeks, since we're in June right now, nothing will happen. So what we do then is wait till the view begins to populate. Obviously, you probably wouldn't put it that far out in the future, but as soon as the view begins to populate and you're safely past this point, you can now insert into insert the older data in, and the way you do it is you put the converse condition or the opposite condition where you take the date times that are less than the 12th of June. So basically what this will do is those rows will get populated in. The result is they will both arrive at the same place in the target table of the view, and you'll get all your data. So that's That's a really neat trick. There are other variations on it. Obviously, you could break the inserts up into pieces. If you have very large amounts of data, you might do it a month at a time, something like that. You can probably think of all kinds of variations. But this solves that loading problem and prevents you from losing data. The other operational issue that I think is nice to talk about today is just how to do schema changes on the views themselves. And I'm going to look at a couple of different cases. So one of the things you might like to do, in fact, this is very common, you put the view out there, it's super fast, and then some analyst comes to you and says, hey, we need more information. So let's say that in this case, we had a sales table, we got the sum of sales, but somebody said, hey, you forgot average. So how do we get that into the view? And this is the basic sequence of commands, and there's two ways of doing it. Depends on which style of materialized view you do. So if you do the old style views with the inner table, the first thing you do is you need to detach that view. And this is basically going to stop the view from operating. So in this case, we now need to actually think a little bit about how we're going to miss updates. So you may have to go refer back to what we just described a few minutes ago. But now we're going to go ahead and update that base table. So that's a real table, even though it has a funny name. So we can go ahead and alter it and add the column amount average. We're going to specifically say it needs to go after amount sum. And you do need to check the order carefully when you're doing this, because if you screw up the order, when the views get populated, if the table order and the view order definitions don't match, obviously you can either get data put in the wrong place or it will just break. And then the other thing, as I mentioned, is you need to think about, okay, can I just stop the inserts for a second while I'm doing this? And that might be reasonable because this is actually going to be really quick. Or you have to load the data later. So these are sort of things that we want to think about. We also then want to go ahead and reattach the view and make it work. And in this case, we now need to change the definition of the view so that we can, so that the view is properly updated with this average state. So we just reattach, and this is a form of the attach command. It's kind of like a create table, but it's just bringing back the materialized view with the extra information. So we've added a column. Those are the three steps. All right. Now, the other style of view, one of the reasons that we favor them is that they're easier to change. In this particular case, if we do the same change, it's much shorter. What we'll do is we'll just drop the view. It's as simple as that. Now, if we had done that on the previous view, it would have deleted the underlying table. That would have been bad. So what we now do is drop the view, alter the update, do an alter table on the target table, and then recreate the view. It's as simple as that. And just flipping back to look at what we have to recreate, another difference is when we were reattaching the view, we had to redefine the engine. So we don't have to do that because that's on the base table and it doesn't need to be changed. So this is just a better way of changing the views, and definitely something you should look at if you're creating your own views. One final question is, how do we add a dimension to the view? In other words, another group by condition in the materialized view. So here's the commands to do that. Again, drop the sales amount materialized view. We're going to go ahead and do an alter table where we're going to add the column and also modify the order to add it in. It turns out in ClickHouse, as far as I can tell, you must do the modify order at the time you do the add column. That's a requirement. But this is the way you do it, and then you recreate the materialized view. So fairly straightforward. And in both this case as well as the previous ones, if you don't have the data won't be populated until more inputs come in. And so for example, if you select and you want to see the customer ID, it'll just show up as 0. Aggregates will show up as the value nan, or not a number. So that's basically what happens there. So at this point, we've covered just about everything on views that I thought we could get into an hour and still have time for questions. I'd like to just do a roundup and then take any Q&A if we have questions remaining. So just some takeaways on the views. Some of the things that we've reviewed today, and as we've been describing views. So first of all, views are basically like an automatic trigger, and that's really all they are, particularly if you use this second way of describing them. So they just move data from the source table to the target. If you use the old style views, where you create the materialized view and let it create the inner table, it also creates and optionally populates that inner table for you. They solve a bunch of important problems. We saw 3: speeding up queries, doing a last point query, and remembering aggregates after the source rows are dropped. So those are 3 things, interesting things that you can do with views. These aggregate functions, it's really critical to understand them. They hold the partially aggregated data. They look funny, but as it turns out, if you go in and look at this and think about, hey, how would we deal with aggregation across massively parallel data sets? So for example, imagine that you have hundreds of parts on each node and you have hundreds of nodes across the system. You need to have some notion of intermediate state. This is exposed in ClickHouse, and once you understand it, it's a very simple pattern and it's pretty easy to work with. We talked about the 2 styles of materialized views, and then we talked about a couple of operational issues. So loading with filters allows you to avoid data loss on busy systems, and then schema migration operations are just, you can do them. We've shown examples of them. They're definitely easier to do with that 2 style target table style of materialized views. That said, there's a bunch of other stuff on views that we don't really have time to get to. We may do these in later talks or blog articles. There's many more use cases. So for example, you can do different sort orders. Because you can change sort orders, you can actually use views as secondary indexes. You can do data transformations. There are others beyond that. Those are just some that we thought about as we were reviewing this. We can talk a lot more about table engines and materialized views, go into more of the details about what they're doing. We didn't talk much about failures. So for example, if you have multiple views per table, how they, since the insert is synchronous and the trigger fires synchronously, what happens if you have a broken view, things like that. And then more tips on schema migration. There's just many more things that can happen out there. We'll get to those in later talks, but I hope that what we covered today gives you a good sense of what's there. So with that, we're done. I'd like to say thank you for your patience. Really appreciate you hanging in here. And before I get to the questions, of which I hope there'll be lots, I want to tell you we do have a special offer. So this is our last commercial, I promise. Please contact us if you'd like to, do an hour. We do that for free. We'd love to talk to people. You can sign up under the URL that's shown on the right side, and we'll gladly spend an hour with you, go over what you're doing, and offer whatever assistance we can. We have some great people. I will tell you that I am the least informed person on materialized views on the team, so you can count on a really great session. With that, I'd like to go ahead and answer the questions, and we have some good ones. Oh, I love these. Okay. This one is great. Is there any use case for the partial aggregated data? Seems seems odd that this level of access is available if there is no use case. An interesting use case is actually you can aggregate it. You can basically take the partial aggregates, the state data, and you can actually aggregate it to create more state data. So, so I don't have an example of that, but I've read the code and it is possible to do this. So there actually are cases where you can actually manipulate. The fact that you can see these partial aggregates gives you the ability to manipulate them. In a future talk, I'll try to provide examples of that. But that's definitely possible to do in the code. And what that means is you can you can, according to the code at least, you can actually chain these partial aggregates without having to pop them back out into a real table. That's a very interesting capability. Have another question. What's the insert speed degradation after adding more than one materialized view to source table? Is it linear or depends on view aggregation? Really depends on the view. So in general, the cost of one way that you can get a sense of what's the cost of the view going to be is go ahead, create the view, run the insert to add the data into the view, and you can think, you basically, if you divide that by the size of your view or the number of rows that were inserted, you can basically get a rough sense of, hey, if I insert 100,000 rows, what's the additional cost going to be of the materialized view? But it's basically linear. As far as I know, because ClickHouse tends to run things in parallel, I haven't checked to see whether the firing of the triggers is parallel. I would guess that it is. It's pretty rare in ClickHouse for anybody to do anything that doesn't run in parallel if it can be, or if it can do so. In your materialized view, you referenced summing merge tree. What's the difference functionally between that and the aggregating merge tree? Great question, and I did refer to that, but I want to reiterate this. There really is no difference other than the fact that the summing merge tree can process this sum aggregate function without having to have one of these partial aggregate functions like sum state. So it's kind of an optimization that's designed to handle the simple case, but the trouble is that I think for most people, that's like just a part of what they do. So people tend to, you can really use aggregating merge tree and there's not a lot of difference. And in fact, if I were constructing views doing the sums, the summing merge tree way with just the sum function and then having some, state functions for everything else, I think that's a little confusing personally. I'd rather do it consistently so that when I look at it, I sort of know what I'm dealing with. So that's basically the difference. But as far as I know, there's no other difference. Let's see. So we have. Let me just run down the questions. I hope we got everything. Oh, here we go. Is there any advantage? Oh, great. Keep them running. Is there any advantage to doing transformations in ClickHouse instead of Kafka? And can we stream materialized data back to Kafka? I'm not a big Kafka person, so that is sort of a hard question to answer. And it actually, let me just say this. I haven't worked a lot on these use cases, but the materialized views can be basically used to, this is one of, some of the folks that we work with actually do use materialized views to create data transformation pipelines. So if you can do it, the question of whether there's an advantage is like, hey, how complex is doing the transformation in Kafka versus setting up a set of materialized views and manage them. Materialized views in general are not that hard to manage. So I think there's some advantages there, but it would really depend on your data. As far as streaming the materialized data back to Kafka, I do not know how to do that. I would think you'd have to read it out, but there's the point of your question is there a way to push it into, for example, like a Kafka table engine? I mean, that's sort of the way you would think about it is, hey, we can trigger into a Kafka table engine and then let that take care of it. But I've never tested it, and I do not know if that's possible. How does the last point view? Yeah, you created the view on top of your AMT table to hide the specialized aggregator functions, e.g. merge sum. Does ClickHouse push down restrictions on the grouping columns down to the AMT table? Yes. So you can actually do, if you change the grouping in your view, yes, it would overwrite it. One thing that I have run into is that sometimes there's various. One of the things you have to test kind of carefully is to make sure that grouping conditions match across for example, across the view definition, across the insert used to populate it, across selects on it. And you can run into cases where if they don't match in the right way, the views will fail. I can't give you general rules for it, but definitely something to test. So just definitely check it. One thing you can do, so maybe a different way of answering this question, is you can't actually, the grouping conditions are set in the aggregation. So for example, if you group by hour and by host, as we did in the CPU case, you can't change that. What you can do is relax them. So for example, you could now, if you wanted to, see, for example, add up things across hosts, you could just drop the host out of the grouping condition, in which case any sum would be computed across all hosts. You could drop them entirely, in which case your sums and your averages and so on and so forth will exactly match the sums and averages that you get when you just run them on the whole source table. How does the last point view using the aggregating merge tree compare to using a replacing merge tree table, either directly or via another materialized view? That's a great question, and I'm going to be honest. I have not used replacing merge tree tables very much. So that one is, if you leave an email, I will gladly get back. I will gladly get back to you on that. So please do leave you can post your email directly to me in chat, and I would love to get back to you on that. As you know, one table can have one primary key. Can materialized view be used to put another table with the same structure but another primary key? Yes. In fact, if I were reading Hacker News, that'd be a big this. That's exactly right. And in fact, that's a use case that I think we really want to talk more about, because what you're really able to do with a materialized view is, I was showing it largely for aggregates and sort of questions related to aggregates, but what you're describing here is you're using a materialized view to cluster data differently. So if you're familiar with, for example, Vertica, which has the notion of projections, same data but ordered differently so that you get different performance characteristics from your query, you can do this with a materialized view. So that is definitely something you can do, and it's a very powerful way to use views, and I hope we'll be able to talk about it in a future talk. Speaking of talks, we're now at 3 minutes over. I really appreciate your questions. For the person who had the question on the aggregating merge tree versus replacing merge tree, please do send us your email and contact us. We'd love to talk further on that point. And for everybody else, I'm going to go ahead and close the talk. Thank you so much for attending today. I hope it's been useful. If you have suggestions for improving this, we'd definitely like to iterate on this talk and get more interesting stuff about materialized views. Please do give us feedback, and we'd love to add improvements to this talk so that it's better next time. Thank you very much, and have a great day.